Hello, good afternoon. Today is the last session of this second conference from the Cátedra Franca de Nanotecnología, the Thursday Nano spin-off talks. Today with José Miguel García-Martín from the spin-off Nanostine. José Miguel is a research scientist from the CSIC in the Institute of Micro and Nanotechnology from Madrid, with a PhD in physical science from the Complutense de Madrid. He was postdoctoral researcher in Paris-Saclay University, France, and Fulbright visiting scholar twice, in the Northeastern University in Boston and also in the NIST, in the National Institute of Standards and Technology in Boulder, Colorado. In 2020, he co-founded the spin-off Nanostine. He is distinguished lecturer by the IEE Nanotechnology Council for this year, and in same communication, he co-directed and co-wrote the documentary 40 años viendo átomos. In 2023, received the awards from the Royal Spanish Physics Society and the BBVA Foundation for the best science communication contribution, and is co-author of the book Las nuevas microscopías, herramientas para la exploración del nanomundo. In this talk, Nanostine is really part 2 because you come before.
One of the other co-founders.
In this part, José Miguel is going to speak about nanocolumnar thin films for a wide range of applications.
Thank you very much. Thank you very much for the presentation and especially for the invitation for being here, presenting the second part of the activity of Nanostine. So these are the 3 parts of my talk. I will explain what Nanostine is, how we manufacture nanomaterials, and then the applications that we have developed so far. So Nanostine is a spin-off of the Spanish Research Council, CSIC. So, well, you are all familiar with CSIC, so I don't need to spend too much time here explaining what CSIC is, but you know that it's divided in 121 institutes, depending on the field of research. And our spin-off comes from 2 institutes in the outskirts of Madrid, the Institute of Micro and Nanotechnology and the Institute of Material Science of Madrid. So our company is located up to now in the campus of the Autónoma CSIC University, but next month is going to move to Alcalá, to another small town in the east of Madrid. So, as I said, we are coming from 2 institutes of CSIC. From the Material Science Institute of Madrid, Ipsutel and Lidia Martinez, they developed the fabrication of nanoparticles using sputtering. And myself, José Miguel, coming from the Institute of Micro and Nanotechnology, I have developed the fabrication of nanocolumns. And then in the founding team of the spin-off, we also have Iván Fernández. Iván has a PhD. He did his PhD in our institute, in the Institute of Micro and Nanotechnology, and he created the first company, Nano for Energy, devoted to the fabrication of hard coatings using sputtering. And so we have been collaborating with Iván for several years, scaling up the processes of fabrication of nanoparticles and nanocolumns. And also we have a consulting person, Miguel Carretero, and it's important to have someone in the company who knows about economy and business, because it's something that as scientists, we don't care so much, but it's very important, of course. So Nanostine fabricates this nanomaterial using a physical vapor deposition technique. So compared with chemistry methods, it has some advantages. Well, chemistry, of course, has an important advantage. It's very cheap. It's very cheap. However, it has some drawbacks that, depending on the application, can be a problem. With chemistry, it is difficult to control the homogeneity in the size of the nanomaterial. Sometimes you have impurities on the surface, or you need to add ligands to avoid agglomeration. And then usually you have recycling problems because you are using some chemicals that can be dangerous. In Nanostine, we work with the physical vapor deposition technique, so we don't have recycling problems. The only leftover is argon, is an inert gas that can be evacuated to the atmosphere. We have high purity material because we work in vacuum, and we have a good control of the size of the nanomaterial. Well, the company was founded in 2020, but it was pushed forward with the Neotech program from the ministry in 2022, which we received €500,000 to have our own equipment that you can see here. Nowadays is at the Institute of Material Science of Madrid, but next month it will be moved to Alcalá. And you can see that we have appeared in the press, in the media, and you can see the 5 founding members of Nanostine and the 3 persons that are working full-time in Nanostine. Starting from the right, the CEO, Daniel González. In the middle, César Rodríguez, who is basically manufacturing the nanomaterials. And the CTO, it was Sandra Cortijo. But Sandra has recently moved to Denmark. So now we have hired another person, Jimena Soler, is now our CTO. And César was doing an industrial PhD in the company, and he passed the exam a few months ago. So now he's also a doctor. So 3 doctors are working full-time in the company. So when you have a PhD, you are not forced to work in academy. You can also work in a company. That's the message. So this is the scheme of the system that we have, and we have 2 patents. One is for the manufacture of the nanoparticles, which takes place in this part of the equipment, and the second patent that we have is for the development of anti-multifactor coating. So those coatings are important to mitigate the multifactor effect, which is an undesirable effect very important for the aerospace industry that takes place in radio frequency devices in vacuum. We will talk about it later. And so what Nanostine can manufacture are single element nanoparticles, alloy nanoparticles, core shell nanoparticles, either with an oxide in the shell, either with another metal in the shell, nanocolumns, and nanocolumns decorated with nanoparticles. All these materials can be produced by Nanostine. The possible elements are here staining in violet. So basically, all the elements that you can sputter with a DC current is what we can use in Nanostine. And the materials that Nanostine fabricates are important basically in three fields: for the aerospace industry, for nanomedicine, and for energy and environment. So now, let's move to the second part, is how Nanostine fabricates the material. So we are using a sputtering. A sputtering is a physical vapor deposition technique in which, with the help of a plasma in a vacuum chamber, we can remove atoms from a bulk material, the target, and by transferring, we create a plasma from an inner gas, then we accelerate the ions towards the bulk, and then by transferring energy, atoms are ejected, and the atoms can be deposited onto the substrate. In this configuration, in which the target and the substrate are parallel, or as you can see in this picture, are quasi-parallel, this was taken, by the way, in an Aja sputtering, similar to the one that you have here at your institute. What you obtain is a thin film. So the atoms are deposited, forming a thin film. And it is widely used in industry because the energy consumption is moderate. It's basically for the vacuum pumps and for the electromagnetic power to create the plasma and accelerate the ions. We don't have recycling problems, and it is a technique that can be scaled up to large areas. So that's why it is widely used in industry. For instance, the hard disks of the computers are made with the sputtering, the photovoltaic panels are made with the sputtering, and even the electrochromic windows of the electrochromic coatings of the windows of the smart buildings are made with the sputtering. You can see here the target, which is 3 meters long, that is used by a Spanish company, Douglas, to fabricate one of the coatings for these windows. So, but this is for thin fields, and we want to fabricate nanomaterials. So how can we fabricate nanoparticles and nanocolumns? So let's start with the nanoparticles. In this case, we are using a sputtering based cluster source, which means that the substrate is not in the same chamber than the bulk. They are separated, and we can have the substrate in vacuum or in ultra-high vacuum, and in the region where the atoms are created, we can have differential pumping, so we can introduce another gas that does not participate in the plasma, but is simply changing the pressure, increasing the pressure. So if you increase the pressure, you are increasing the probability of collisions. So while the atoms are traveling, they start colliding and forming clusters. So if you separate these two chambers by a pinhole, you have a beam of nanoparticles on the second chamber. This is what my colleagues at the Material Science Institute of Madrid, Yves and Lydia, have developed. And you can see that they have achieved a very good control of the size of the nanoparticles with a narrow size distribution, just with the parameters of the sputtering. And in fact, they have a patent using a multiple target cluster source. So they are able to fabricate different kind of nanoparticles. Single element nanoparticles, when only one of the targets is switched on, we have single element nanoparticles. Then if we put two of the targets at the same distance from the pinhole and we switch on both of them, we can have an alloy nanoparticles, but then we can retract one of them. So we increase the distance to the pinhole. So first, we have clusters of the red material, let's say, and when they go in front of the yellow material, they are coated, forming a core shell nanoparticle, in which the core is red and the shell is yellow in this scheme. But we can do the other way around. We can retract the yellow and put in front the red. So we have the complementary core shell nanoparticle. And this is another difference compared to chemical material, because with chemical synthesis, you can have only one of these core shell nanostructures. For instance, if you're using electrochemistry, these metals have different reduction potential, so only one of them, of these core shell structures, can be produced, because in electrochemistry, you work with in equilibrium conditions, whereas we are not limited by that in this physical method. But okay, that's all I'm going to say about nanoparticles, because you have a first talk about this 4 years ago, given my colleague Yves Soutel in this Cátedra SAMCA in April 22. You can revisit this talk if you are interested in the formation of nanoparticles. So I'm going to talk about the second kind of material, the nanocolumns, that we can fabricate at Nanostine. What we have to do is we need to tilt a lot the substrate with respect to the target. So we work in glancing angle deposition, and by so doing, we are favoring self-atomic shadowing mechanisms that I will explain in a minute. And as a result, you can see that we have tilt nanocolumns. This is a top view image. This is a cross-section SEM image. So you can see the scale is 250 nanometers. So the typical diameter is tens of nanometers, 30, 40, 50 nanometers. And we can only control that within a certain range, because it depends on many self-control mechanisms that I will explain briefly. However, we can control easily the length of the nanocolumns with the deposition time. So, as we have tilted the substrate, let's assume that all the atoms are ballistic, which means that they are traveling from the target to the substrate without suffering any collision. So the first atoms arrive randomly at the surface. The next atoms have a certain probability of being placed on top of some of the initial ones. And when they do that, they create a shadow region behind them that I have a staining gray. If all the atoms arrive with this direction, they cannot be placed in the shadow regions. So a competitive growth takes place. Finally, let's say that the small mounds fall in the shadow of the bigger pillars and they stop growing. So that's why at the end, if you have a look at the cross section, you have at the beginning some small pillars, but at the end, all of them are having the same length, because the smaller one stop growing. So this is the self-atomic shadowing mechanism. But in reality, it's not so simple. First, because I'm assuming that the substrate is perfectly flat, which is not in reality what happens. So the process usually takes some nanometer to be fully developing. And then in sputtering, we also have some atoms that can arrive with another direction. Why? Because they can suffer collisions with the species of the plasma, typically with the ions. And as a result of these collisions, they can lose energy and they can lose directionality. So this is one of these atoms. So this atom, as a result of collision, can arrive with other direction, and in particular can be placed onto the shallow regions. And when that happens, the columns become wider and more vertical. So we can control the balance between the ballistic atoms and the thermalized atoms with the pressure in the chamber. The lower the pressure, the more favored ballistic atoms are, because to decrease the probability of having collisions. When you increase the pressure, you increase the probability of having collision, then you increase the amount of thermalized atoms. So let's say that when you increase pressure, you can assume that the columns are going to be wider and more vertical. And this is experimental proof of what I have just said. We fix the tilt of the substrate at 85, so glancing angle deposition. We are sputtering gold, and we are just changing the pressure in the chamber. So with the lowest pressure, we could maintain the stable plasma, 1.5 10 to the minus 3 millibar. Those were the columns. By increasing 1 order of magnitude the pressure, you see that the columns become wider and more vertical. If we further increase the pressure, you can see, again, wider and more vertical. In fact, there is so much coalescence between neighboring columns that instead of a nanocolumnar thin film, in this case, we can say that we have a porous thin film. So, as a rule of thumb, if you want to have nanocolumns by sputtering, you need to work with high tilt angle, above 75 degrees, and with low pressure, typically in the 10 to the minus 3 millibar range. In the international system of units is 0.1 Pascal. Then you may wonder, can we have vertical pillars, but without having a strong coalescence between neighboring columns? The answer is yes, if you add another parameter. If you need rotation, the red light is blinding, so I think we don't have battery now. Okay, so I have to change my position so I can control it from here. Okay, so if we now add rotation around this axis while we are depositing, we can have vertical pillars. So I have colleagues at the Material Science Institute of Sevilla, and they have developed this model to explain the growth of the nanocolumns. They have taken into account the ballistic atoms traveling without suffering collisions, the thermalized atoms that do suffer collisions, and they have defined a thermalization degree, which is given by this expression, where P is the pressure, L is the distance between the target and the substrate, and G is this quantity which depends on the cross-section, the thermal energy, and nu. And nu indicates the number of collisions that are required to completely thermalize one atom, which depends on the atomic mass of the element. So if we work with a light metal, such as titanium, just 3 collisions with argon ions are enough to completely erase the initial directionality of the atom. However, if we work with a heavy metal, such as gold, we need more than 10 collisions, around 12, to completely thermalize this atom. And another thing we have to take into account are hyperthermal processes. Why we call them hyperthermal? Well, we are working at room temperature. Room temperature, the energy is 0.02 electron volt. But in sputtering, the atoms arrive at the substrate with at least 10 electron volt, which means at least 2 orders of magnitude higher, or 3 orders of magnitude higher than the thermal energy. So the atoms can do things when they arrive at the surface. What can they do? Well, they can diffuse along the projection of the initial momentum till they find an obstacle. This is called bias diffusion. Another thing they can do, they can transfer kinetic energy to an atom that is already there and move that atom if there are positions available. This is the kinetic energy induced mobility. And you will see that there are differences if this atom relaxes to a random position or if it relaxes to the most coordinated position, which is the position in which it's going to have the maximum number of neighboring atoms. But in any case, these two mechanisms act as dragging mechanisms that are going to push in the vertical direction in the columns. So the columns always are less tilt than the tilt of the substrate during the deposition. Well, you can see here a comparison for 4 different metals between the experiments for gold, platinum, titanium, and tungsten, and the results of the model, assuming on the right that in the kinetic energy induced mobility that the atom relaxes towards the most coordinated position, whereas in the left, if we assume that it's going to move to any position, random movement. So you can see that in the case of gold and platinum, it is the most coordinated relaxation model, the one that explains well the experimental result. However, for titanium and tungsten is the opposite mechanism, is a random relaxation, the one that explains better the morphology of the real films. The reason, we don't know it yet. So it's a phenomenological model, but we haven't found the reason for this. At the beginning, we thought it was the atomic mass, but then when we work with chromium, that is not shown here, but chromium is very similar to titanium, but however, it relaxes as gold. So we still need to explain why. But the model works very well. And it works very well, not only explaining the tilt of the columns, but also the density of the films. So you can see here, beta is the tilt of the columns, alpha is the tilt of the substrate, in red is the model assuming relaxation towards the most coordinated position. You can see that it explains very well the tilt of the columns, but also the density of the films. In the case of gold, using the most coordinated position model. On the contrary, for titanium, the experimental dots are in white. You can see that is the model in blue, that is the random relaxation model, the one that explains the tilt of the columns and also the density of the films. And then you can see these black squares are experimental results, but using another physical vapor deposition technique, evaporation, thermal evaporation. And it's very different. You can see here, it's the same material, titanium. This is with the sputtering, and at the bottom with evaporation. You can see that with evaporation, the columns are much thinner and more tilted. This is what, and the reason for this is that in thermal evaporation, depending on the sublimation temperature of the elements, the atoms arrive with an energy of tenths of electron volts, 0.2, 0.3, much lower than the 10 electron volt with the sputtering. So in fact, what my colleagues in Sevilla did to explain this, they switch off the hyperthermal processes, they switch off the kinetic energy induced mobility and the bias diffusion, and they obtain the model in green. And you can see that this model explains quite well what happens with evaporation. So high porosity and thin columns and tilt columns. So the message is that you can also fabricate nanocolumnar thin films with other physical vapor deposition technique, for instance, with evaporation, but the results are different. And we are interested in sputtering because sputtering, as I talked at the beginning, is a really scalable technique that can be used in industry. You cannot cover large areas with nanostructures using thermal evaporation. It's very expensive, nobody does it. Okay, so now let's move to the third part of the talk, to the applications, and I will give a brief overview of all these applications that we have developed up to now for energy and environment, black metals, improving the performance of perovskite solar cells and self-surfaces. In the aerospace industry, the anti-multifactor coatings. In biomedicine, as antibacterial coatings for orthopedic implants, bioelectrodes, for the detection of molecules with electrochemistry, or for the detection of molecules with surface-enhanced Raman scattering, and finally magnetism. So let's start with the energy and environment. The first application was a black metal. In particular, we were sputtering gold. And this is a photo of two films. The one on the right, fabricated with 75 degrees of tilt angle during the deposition, and the one on the left with 87. And we were rotating while we were depositing. So you can see the SEM cross-section images. If you look carefully, you can see that here there is a wide distribution of sizes, because we were still at the first regime of the deposition, while the small structure were still growing. So we have a wide range of sizes, and as a result, we have a wide range of frequencies in which we can excite the localized surface plasma resonance of this gold nanostructure. As a consequence, the reflectance spectra of these nanocolumns is here in black. You can see that in the visible range, the reflectivity is below 10%, because the light is being used to excite the localized surface plasma resonances of this gold nanostructure, and these combined with a multiple scattering effect gives rise to this low reflectivity. So this can be used for applications in radiative heat exchangers, separators in optical devices, thermal light emitters, or even in the solar energy absorbers in the thermosolar power plants. So you have mirrors that are pointing all the reflected beams towards a point which absorbs a lot of light. So we can use this material at that point. Second application is to increase the performance in perovskite solar cell. This is the typical structure of a perovskite solar cell. We start from a transparent conducting oxide, typically fluor tin oxide or indium tin oxide. Then we have a transparent electron transport layer, typically made of titanium dioxide. Then the active material, the perovskite, and finally the whole transport layer and the gold electrode. The idea is that the light comes in, creates an electron hole pair, and then you take the electron through this. You take the electron to this electrode and the hole to this electrode. You separate the electron and hole pair. That's why you have electricity. So our idea was to add here nanocolumns, titanium dioxide nanocolumns, and in fact, with the help of a mask, in each sample we had two solar cells. One just with the compact titanium dioxide, and on the other side, on the other half of the sample, with the nanocolumns. You can see here a picture of one of these samples. So you can see that in the half with the nanocolumns, we are losing some transparency, but we will be winning something that you will see in a minute. So the quality of the perovskite that is deposited on top of this is not affected by the morphology. So the perovskite is a paste that is deposited by spin coating, and you can see that the crystalline structure on top of the nanocolumns in red, or on top of the flat titanium dioxide in black is the same. So we are not changing the quality of the perovskite, but we were winning something, and what we win is a higher absorption in the visible and in the near infrared range. As you can see, with the columns is in red, and we increase the absorption. And the reason for this is an optical effect in the near field that we can measure with a scanning near field optical microscope. It can be an optical fiber, or it can be, as in this case, a fluorescent particle at the apex of an AFM proof. But the thing is that this is like an AFM, but at the same time, we can measure the optical signal. So when we do a scan on top of the flat titanium, you can see nothing in the topography and nothing in the optical signal. It's not interesting. However, on top of the columns, you can see the topography. We have some rugosity. We have a lot of convolution with the fluorescence particle, but we can see that we have some corrugation. And in the optical signal, you can see maxima and minima. And the maxima are regions where the light is concentrated. So now, if we now scan in a plane like this, in a vertical plane, this is what we obtain. So the apex, the top of the nanocolumns would be here, and you can see that the tails of these maxima go up to hundreds of nanometers. This is in micrometers. So this is 200, 400 nanometers. So the perovskite that is placed on top of the nanocolumns, in particular the ones that are placed on top of the regions where the light is maximum, are going to increase the power conversion from light to electricity. That's why at the end, the efficiency of the whole cell changes from 15.3% without the nanocolumns to 16.4% with the nanocolumns, which is a 7% relative increase. So now the third application, and continuing with the solar panels, is self-cleaning. The idea is that we would like to have a surface that can be cleaned by itself, because typically the regions where we have a lot of sunlight along the year are desertic regions, regions with a lot of dust in the air, in suspension. So that's why you need to clean them using water, but water is an expensive resource if you are in the desert, or you have to hire someone who cleans it manually. So that's why it would be great to have something similar to what nature does in the lotus leaf effect. So first, you want to degrade the organic dirt that is deposited on top of the solar panel. And for this, you can use the UV part of the spectra of the solar spectra. And then imagine that you are able to do what the lotus leaf effect does. What the lotus leaf does is that the water does not spread, but is condensated in the form of droplets. So if you can condensate a droplet in your photovoltaic panels, as the panels are always tilted because they are looking at the sun, this droplet is going to carry the dust that you have degraded, and then it's going down the slope, and then it's self-cleaned. That would be great. Okay, so, and if you look at the lotus leaf with an SEM, you can see that they have a double periodicity, micrometer pillars with a correlation in the nanoscale. So we want to mimic this behavior, combining nanocolumns and nanoparticles. We have already achieved the first part. I will show you now how we have degraded an organic pollutant, and now we are working on the second part. So the best degradation that we achieved was using titanium dioxide nanocolumns decorated with gold nanoparticles. You can see here SEM images. The one on the below is taken using the backscatter electrons detector, and the number of backscatter electrons depend on the atomic mass of the element. So all the bright spots correspond to gold nanoparticles. So you can see clearly where they are. However, with the standard secondary electron, it's difficult to locate where the nanoparticles are. And this is the top view image in which we have just stained in yellow with the software, the gold nanoparticles. And so as an organic pollutant, we have used a model material, which is the solid stearic acid. And you can see here the infrared spectra of this organic pollutant as a function of the irradiation time with the solar simulator spectra. You can see that the intensity of the peaks decreases, which means that the material is being degraded. And we can integrate these peaks, and we can plot these curves as a function of the irradiation time. In blue is the curve with only the titanium dioxide nanocolumns, because this is the active material. But when we decorate them with the gold nanoparticles, you can see that the degradation improves. And the reason is something similar to what happened in the solar cell. We are helping to separate the electron hole pair created in the active material, in the titanium dioxide. So gold helps to increase the lifetime of this electron hole pair. So the electron is there more time to participate in the redox reaction that degrades the pollutant. And as I said, we are now working on the second part of the problem. We are working in tuning the wettability, and this is measured by putting water droplets on top of your surface and measuring with a camera, taking a picture and measuring the tangent of the angle of the tangent with the surface. So when the water spreads, the contact angle is below 90, so you have an hydrophilic surface. 90 is the frontier. If you have an angle that is higher than 90, it means that you have more than half a sphere, you have a hydrophobic surface. So in our case, the titanium dioxide nanocolumns by themselves are already hydrophobic with 140 degrees of water droplet. But then when we add the gold nanoparticles, we increase to 114, 10 degrees more. Now we are studying other combinations. For instance, just showing one example here with gold nanocolumns, with gold nanoparticles as a function of the percentage of coverage with gold nanoparticles. You can see that we start with 107, and then we saturate at around 145 degrees, where we have more than one single layer of nanoparticles. And so the idea is to mimic the lotus leaf effect by having two periodicities. In our case, one periodicity is given by the columns, the other by the nanoparticles. So now we move to the aerospace industry. In this case, we have developed coatings that mitigate the undesirable multifactor effect. And what is this effect? Imagine that you have a waveguide in vacuum, so in a satellite or in the International Space Station. And then you have one charge there. Typically, you have many charges because we have the solar wind. So imagine that you have an electrode, and this electrode is going to be accelerated by the radio frequency field, because this phenomenon takes place in radio frequency devices in vacuum. So it is accelerated by the radio frequency field, and when it crushes the walls of the waveguide, it creates secondary electrons. These secondary electrons start with low energy, but then they are accelerated by the field, and when they crash, they create new secondary electrons. So at the end, you can have a cascade of secondary electrons. So in the least dangerous scenario is just an electromagnetic noise that perhaps can prevent the communication with the satellite. But in the worst case scenario, if it exhibits high intensity, it can physically damage the device. And this is what you can see here. This is a picture given by the European Space Agency, and you can see that in the edges of this waveguide, we can see damage that the material has been burned. So one possibility to decrease this phenomenon is to have a corrugated metallic surface in the nanoscale. So when the new secondary electrons are created, they can travel just a short distance, which means that they can be accelerated just a short time. They can win energy just a little till they crash again. And as the new secondary electrons always start with low and low energy, if you don't give them enough space or enough time to be efficiently accelerated, the phenomenon disappears. The way to measure this phenomenon is by measuring the secondary electron emission yield as a function of the energy of the primary electron. And typically, this is the shape of the curves, and there are two parameters that you want to tune. One is the maximum of the curve. You would like to have it as low as possible. And the second important parameter is the crossover energy with the value 1. Because for energies lower than that crossover energy, you have less, in average, less than one secondary electron emitted per primary electron. So the phenomenon disappears. So here are the best coatings that we have produced up to now. They are made of silver nanocolumns, but that we have capped with gold. We have capped with gold to prevent oxidation, because silver oxidates in ambient conditions. This is something that our grandmothers knew. They were always cleaning, the cutlery to remove the oxide from the knives and forks. So, and here I am comparing the secondary electron emission yield curves in black for this coating, and in green for two reference material used in the aerospace industry. So you can see that the first characteristic that we wanted to achieve, the decrease of the maximum, is clear. And now we will focus our attention on the low energy part. You can see that the coating with the highest crossover energy is the one with the nanocolumn. So we have increased the range in which we have less than one secondary electron emitted per primary electron. So the other characteristic that we wanted to achieve. So now we move to biomedicine. So in biomedicine, we have developed 4 applications. The first one was antibacterial coatings, and we were again, mimicking nature. In particular, the wings of the cicada, when we look at them with an SEM, they are made of nanopillars, and they are antibacterial. Bacteria cannot proliferate in this surface. The pillars are made of collagen and lipids, but what is really important is the morphology. So our idea was to coat orthopedic implants with titanium nanocolumns, and the idea is that the bacteria cannot attach, whereas the cells that are much bigger can do proliferate. So these are the SEM images. So this is 500 nanometer. The typical size of a bacteria is around 1 micrometer. So let's say that one bacteria would like to be here, but this bacteria is going to have only a few points to anchor to the surface, the apex of the columns. So it's going to be quite unstable and quite uncomfortable. And that's why we achieve the antibacterial behavior. So we are culturing on purpose bacteria, in this case Staphylococcus aureus, during 1 day. And we are going to stain in blue the extracellular matrix of the bacterial biofilm. So onto the initial implant without the coating, this is what we have after 1 day. Big blue islands, so big infection in this region. But even in those ones, when we make a zoom, you can see blue dots everywhere. Green dots are alive bacteria, blue dots, bacteria that have produced the bacterial biofilm. So infection is being developed everywhere. When we do the same experiment with the same zoom level onto the implant with the coating, you see there is no blue. So we still have some alive bacteria, and when we do a careful counting with the software, it's typically 1/2 or 1/3, between 1/2 and 1/3 of the number of bacteria that are attached to the naked implant. So we are decreasing the addition of bacteria. Besides that, the bacteria are uncomfortable and they cannot interact efficiently to form the bacterial biofilm. Another application is for bioelectrodes. We would like to perform in vitro electrical stimulation, but I will show you just results in physiological media, but without cells up to now. So what we are going to do is we will compare in electrochemical impedance spectroscopy the performance of nanocolumnar electrodes of the same metal, but in thin film shape. So standard flat electrodes compared to columnar electrodes. So, and we have done the study for 3 different metals: gray for titanium, orange for gold, and green for platinum. Closed symbols are the nanocolumns, open symbols are the thin films, and this is the impedance spectra in logarithmic scale. So you can see that for the 3 metals, the nanocolumns exhibit much lower impedance than the flat thin films. And this is good because it means that you can perform electrical stimulation with lower currents. If you have lower impedance, you can apply lower voltages. And the other good thing is that we can transfer more faithfully electrical signal. What does it mean? We will transfer signals using an electrical external power source. But then the electrode will transfer the signal in the physiological media, and those signals can be different. So as you can see here, in blue is the voltage that we apply to the electrode with the external power source. In this case, square pulses. And in green, you have the response of the electrodes, what the electrodes deliver to the physiological media. In the case of the thin film, it's the dotted line, and you can see that the profile is quite different, especially in this region, compared to the blue line. So we are losing the control of the electrical signal. When we use the nanocolumnar electrode, it's the continuous line, and you can see that the shape of the curve is much closer to the shape of the curve that we were applying to the electrode with the power source. So this is important because in electrical stimulation, usually you work with the stem cells and you want to apply certain signals, electrical signals, to guide the differentiation of the stem cells towards the desired cell line. So that's another good characteristic of the nanocolumnar electrodes. A third application in the biomedicine field is the detection of molecules. In this case, we would like to detect dopamine. In this example, dopamine is the so-called molecule of pleasure because it's involved in the regulation of our mood. So the idea is that in the standard 3-electrode cell. In the working electrode, we will have our nanocolumns, in particular titanium nanocolumns, on top of graphene, on top of a copper substrate. And we will use two typical signals, the two typical types of measurement, cyclic voltammetry, voltage as a function of time having this shape, and this is the typical response of the current as a function of the voltage. And we can focus in one of the peaks, and we can then perform the square wave voltammetry with this profile, and this is the typical shape of the curves. So with cyclic voltammetry, this is what we got for two different scan velocities, and you can see that we in the oxidation branch we can see three peaks. One is the oxidation of the titanium nanocolumns, but the other two peaks correspond to transition of the dopamine electrooxidation cycle. And in the reduction branch, of course, we have three peaks, two reductions of this cycle and the reduction of the nanocolumns. Then now we can focus on this peak, on the oxidation 1 peak, and we can perform a square wave voltammetry by decreasing the concentration of the dopamine. We started with 400 micromolar, and we went down to 10 micromolar, and with 10 micromolar, we still were able to detect the peak. In fact, the limit of detection was of the order of 7 micromolar. If we want to go to a further, to lower concentration, we have to use another technique. In this case, surface-enhanced Raman scattering. This is a technique based on the vibrational spectra of the molecules. Imagine that my two hands, my two fists, are a molecule. These atoms can vibrate like this, or they can vibrate like this. These are two different vibrational states with different energy. So in a Raman spectra, we illuminate with coherent light. The majority of the light goes through without suffering any scattering, but a small amount of the light, less than 1 part per billion, suffers a scattering with these vibrational states. So for instance, you can start with a deep state, with the light, you go to the virtual level, and when it decays, you can decay to a higher energy level. So the scattered light has lower energy than the light we were using for the illumination. But you can have the other situation. You can start with an excited state. With the illumination, you go to the virtual level, and then you can decay to a deeper state. So at the end, what you have in the Raman spectra are peaks well located at given positions that depend on the transition between the vibrational states. So a Raman spectra is a fingerprint of the existence of a certain molecule. So, but as less than 1 part per million of the light is suffering this scattering, you need to amplify the signal. And one possibility is to use a corrugated metallic surface, and you can take advantage of the localized surface plasmon resonance of the template. So for this experiment, we were using the gold nanopillar, the vertical nanopillars, and you can see the extinction spectra here, which exhibits a peak for the wavelength in the green. So if we use a green laser, we will excite the localized surface plasmon resonances of these gold nanocolumns. So in this case, we would like to detect thiophenol, which is a molecule used in pharmacy, in the pharmaceutical industry. And you can see the Raman spectra of thiophenol. The peaks correspond to thiophenol, and we are decreasing the concentration. We started with 1 millimolar, and we decreased down to 10 nanomolar. And we were still able to detect the peaks of the thiophenol. In fact, the enhancement factor, thanks to these nanocolumns, gold nanocolumns, is almost 9 orders of magnitude. And the reason for this enhancement is a plasmonic effect. So again, with using the scanning near field optical microscopy, we can see the topography, and we can at the same time detect the optical signal. And you can see that in the interspace between neighboring columns, for instance, this space between these 4 columns is this one, is a region where the light is concentrated, or here, for instance, or here. So we have what we call hotspots, regions where the light is concentrated. So when we put a droplet of the solution on top of this template, the molecules that fall on top of one of these hotspots are going to have the Raman signal amplified. And that's why we achieve such a good detection. And the final application is in magnetism. So in this case, we will work with iron. So we can fabricate tilt iron nanocolumns, or we can rotate while we were depositing, and then we can have vertical iron pillars. And these two materials exhibit different magnetic properties. So we will measure the hysteresis loop along 3 directions, 2 in the plane of the substrate, in black along the projection of the axis of the nanocolumns, in red in the transversal direction, and in violet in the perpendicular direction to the substrate. So these structures are asymmetric in the plane, so they exhibit different behavior in the plane. In particular, the easy axis, the easy magnetic axis, is along the transversal direction. And the reason for this is that in the transversal direction, we don't have the atomic shadowing. The atomic shadowing is in the longitudinal direction. In fact, you can see here that we have coalescence in the transversal direction. You can see that in some regions, the columns have coalescence. You see? So that's why we have an anisotropy in this transversal direction. Now, if we focus our attention on the perpendicular hysteresis loop, is a tilt hysteresis loop. And this is quite different to what happens when we have the vertical pillars. In this case, in the perpendicular hysteresis loop, we have in the central region some squareness, which is coming from the vertical shape of the pillars. And now the loops in the plane are equivalent because all directions are equivalent in this case. And then we can do more, we can do funny things. For instance, we can use a mask while we are depositing, and we can deposit from one side of this tunnel or from the other side. So during the deposition, the substrate was in the middle of the tunnel. I just remove it a little to take the photo. And then by using this mask, we can have vertical pillars, but asymmetric in the plane. So they are elongated along the direction of the axis of the tunnel. So this is a top view image. You can see that this is asymmetric and it's vertical. So in fact, the shape is like an inverted truncated cone. And you can see here the loops, the experimental loops. So we have an asymmetry in the plane. So we have different loops in the plane. And as we have a vertical shape, we have a certain squareness in the perpendicular loop. So the take-home message is that we can tailor the magnetic properties with the morphology. So now we are finishing. Just I would like to mention the funding, typical funding from the European Union, the national government, but we also had funding from a private foundation for the orthopedic implants, Fundación Domingo Martínez. We got an award from the M+ Vision Consortium formed by the regional government of Madrid and the Massachusetts Institute of Technology, the MIT. And as a result, I went to Boston, and then I met people there. And finally, with a full-rate scholarship, I went to Boston to improve the performance of the antibacterial coatings. And we have had funding from the NATO, from the Science for Peace and Security program for the magnetic nanopillars. And I would like to thank IEEE because I have been distinguished as a distinguished lecturer for the Nanotechnology Council. And of course, I am summarizing the work of many people and along 15 years, not only in my institute, also with the Yves and Lydia at the Material Science Institute, a hospital, Material Science Institute of Sevilla, Complutense, Politécnica, Universidad de Oviedo, Indrea Energy, Autónoma, Nano for Energy, and also in institutions in other countries, in the United States, in France, Italy, Greece, Brazil, and Chile. And finally, of course, all this, let me just summarize that we can, with glancing angle deposition with the sputtering, we can fabricate these nanocolumnar thin films with different morphology depending on the material and the growth parameters, and that we have developed applications in energy and environment, for the aerospace industry, for biomedicine, and for magnetism. And I would like to finish saying that, of course, we have transferred all of this to our company, to Nanostine. Also, what my colleagues Yves and Lydia have developed with the nanoparticles, and that's why Nanostine's activity has taken place in these 3 different fields with these companies or institutions in aerospace with the European Space Agency, CNR, with the INTA and LIDAX, in the sector of the energy with Natrion, B5 Tech, Autonomous University and Nano for Energy, and with sensors with Acciona, ITEFI, Graphenia, and ISON. And with this, I would like to thank you for your kind attention. Thank you.
There is time for a few questions.
My name is Pavel. I'm just responsible for sputtering here in adjusted that you mentioned.
Yes, I saw the equipment.
I have one question related with the mechanical stability of the nanocolumns you grow, and especially relation with the lithography process, and it's stable for example, for lithography to define their areas, and if we can use, for example, lift-off techniques or
well, the materials, for instance, they can sustain sonication without problem. They can also sustain autoclave, that is widely used for the biomedicine. No? But we have just started to measure the mechanical properties. We know that the mechanical properties of the nanocolumns are not as good as of a bulk thin film, of course. The Young modulus is about 1 order of magnitude smaller. This is what I can say up to now.
I was surprised, especially with the gold nanocolumn, black gold, with enhanced absorption, wide range by this nanostructure. Really impressive.
Thank you. In the case of gold, depending on the application, sometimes we need to start with titanium just to increase the addition, because depending on the substrate, for example, typically with dielectric substrate, because this black gold we have done it onto silicon substrate, but also in glass. And for glass, you need to add at the beginning a little bit of titanium. So you can start with a small titanium nanopillar and then continuing with gold, because it improves the addition a lot.
In my case, I have particular applications when you couple this gold nanocolumns with gold layers. So you have both thin normal thin layer of gold. You want to continue with the.
Yeah, it shouldn't be a problem if you want to continue gold on top of gold. It works okay.
Thank you. Yeah, very nice, very interesting. Also for our group in particular, we are working in the research, so we have an interest in your coatings. And I was wondering, it's linked to the previous question about the substrates for the deposition, because right now we are moving to soft substrates, flexible substrates instead. So we are doing the deposition on things like polycarbonate or MMA. Well, how's the addition? Did you test this on?
We haven't tried it. It's something that we have submitted a national project, and it's one of the things that we would like to do.
Okay, you have a collaborator here. So you have the collaborator here. That's good.
Okay, thank you.
Oh, sorry. Okay, we are not.
No,
So thank you very much also for your talk. It's quite impressive. All this progress, all these nanoparticles, wires, different shapes of this engineering is really affording. So I didn't quite get your snow signal. Because the snow, you focus some light into the deep apex cavity, right? And you observe the absorption of this light. So you see bright spots in between the colors. Shouldn't they be on top of the polymers? I mean, if I think of I don't know.
No, it's like in the case. Well, it depends on the metals or in the dielectric. I mean, because in the titanium dioxide columns, the light is on top of the columns, but in the metals, it's in between metals. It's something that is well known. It's like an antenna effect. So, for instance, when you have two gold nanoparticles and you approach them at a certain distance, you start having there the hot spots in the interface between neighboring. It's a small gap between neighboring metallic.
But I don't really understand it when you see it bright.
Well, bright it means more intensity, more light intensity. This is what means bright. Is that because you have, in this experiment, it was done in Paris, they have a fluorescence particle at the apex of the AFN tip. So at the end, what you get is the light emitted by the fluorescence particle that depends on the light that this fluorescence particle is receiving.
The medical application also related to the mechanical.
Yes,
Sorry. I was curious for the medical applications and also related to the mechanical properties. Because if you say implant, I imagine, for example, joint, and then like for the friction and the stuff.
Yeah, it's not good for a joint. It's a very good question. No, it's good for. I will show you. It's good for this. It's good for what is called a fixation plate, because we need a flat surface. So if we have a joint or if we have a hip implant, you have complicated shapes. You can do it, but then you need a good collimator, because at the end, a tangent, you have to define a tangent. Okay, then you need to collimate a lot, and then you need a motor and so on. So it complicates a lot the deposition. But in this case, in an implant that those implants are used when you broke, for instance, your leg by skiing, and both the tibia, the peroné, I don't know how to say that in English, but you have an open fracture. And in that case, because for a typical implant, for a hip implant, the ratio of infection is about 3 to 5%. So let's say that 1 every 30, 1 every 20 is infected. And if we remember, our old king, Juan Carlos, had a hip implant that had to be replaced because he had an infection. Maybe you remember that from the media. But so that happens. But when you have an open fracture, the ratio of infection is 20%. So 1 of each 5 is infected. So the idea, this is what you have. At the end, this is just used to maintain the bones fixed. That's why it's called a fixation plate. But when you start walking, it's really the bone, the one that carries the mechanical load. It's not the fixation plate. So that's why for this, because this is flat except region near the holes, and you don't suffer the mechanical load. That's why for this kind of implants, our technology is good for the fixation plates.
Question? No, let's try again.